Okay, let's continue talking about relationships within triangles. Last time we talked about perpendicular bisectors, and we learned about the circumcenter within the triangle. Today we're going to talk about what angle bisectors are. So recall that an angle bisector, such as ray KM here, ray KM is a ray that bisects angle LKJ. And remember, bisect means it splits it in half, so that would make angle LKM congruent to angle JKM. So we'll talk more about the properties of angle bisectors, and we'll take a look at what happens when we have angle bisectors within all three angles of a triangle, and find out what happens when those lines meet. So let's begin by just taking a look at the definition of an angle bisector and what we know about it. So remember that an angle bisector is a ray, as I talked about, divides an angle into two congruent adjacent angles. Recall that a distance from a point to a line is the length of the perpendicular segment from the point to the line. So our diagram here, PS is the bisector of QPR. Distance from S to line PQ is SQ, where SQ is perpendicular to PQ. Same as SR, that's perpendicular to line PR. So the angle bisector here, if a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. So if AD bisects angle BAC, and DB is perpendicular to AB, and DC is perpendicular to AC, then DB will be equal to DC. Those two segments will be congruent. Then the converse of the angle bisector theorem, if a point is in the interior of the angle and is equidistant from the sides of the angle, then it lies on the angle the bisector of the angle. So if DB is perpendicular to AB and DC is perpendicular to AC, and DB is congruent to DC, then AD bisects angle BAC. Okay, so those are properties of the angle bisector that we'll work with. Let's now take a look at how we can construct this. If you have a compass handy, why don't you follow along? So if you've got an angle, any angle, it doesn't matter. Let's put our compass point on the vertex of the angle and just make an arc. Okay, make an arc that intersects both rays of the angle. From there, we take our compass point, and from the intersection of the arc and the ray, we'll make an arc out by the interior of the angle. We're going to keep our compass the same measurement and arc again. And where those arcs intersect, that's going to give us our angle bisector. Okay, so if I take my straight edge and draw from my vertex through that intersection, that'll give me my angle bisector. Okay, so hopefully you can see why that works. Really what we're doing is creating congruent triangles. Okay, so we made our arc out to this line and made an arc that way. That's the same arc. Then we made another arc. It's the same distance. So we have a side, another side. Here's another side that's the same length because we arced it the same. And then we've got that shared side. So really we have side, side, side congruence, which guarantees that everything's the same measurement, which guarantees that these angles, because corresponding parts of congruent triangles are congruent, so we have corresponding angles congruent. So this angle down here would be congruent to this one. And therefore, we would have the angle bisector. Okay, so let's apply our knowledge of angle bisectors to find some measurements. So we want to find a measure of GFJ. Highlight it in red here. Well, I see that GJ is congruent to HJ. and they're both at right angles. So I can see that that's an angle bisector. So if JFH is 42, I know the measure of angle GFJ also has to equal 42 degrees. Okay? And now for what value of x does P lie in the bisector of A? Well, in order for it to lie in the bisector, BP would have to be congruent to CP. So x plus 3 would have to be equal to 2x minus 1. Do some algebra, and I get x equal to 4. In order to make those two congruent. All right, so now we're going to take a look at the angle bisectors within a triangle. So if we go down to GeoGebra, and we can take a look at what's going on when we plot the angle bisectors in a triangle. So on this particular app, we've got a triangle. Hi there. And we've got the angle bisectors constructed on GeoGebra. You can see going from C through D, B through D, and A through D. Notice those angle bisectors when I have them on there. Okay, you can see that those angle bisectors, all their lines meet at one point. Remember, we call that a point of concurrency. It's where all of those lines meet, and it could be inside the triangle, outside, or could even be on the triangle. In this case, it's inside the triangle. Okay, so I'm going to drag those points around and see what happens to that point of concurrency. So right now I've got an acute triangle. Let's make a right triangle. Notice it's still inside. If I make an obtuse triangle, try that. We still have that point of concurrency within the triangle. And doesn't it make sense that it's always going to be inside the triangle, because those angle bisectors always go in between the angle it's bisecting. So there's no possible way that it would be outside. So it'll always meet inside the triangle. We call this point the incenter. Okay? And I'll show you why it's called the incenter in just a moment. Prepare to be amazed. Remember, the perpendicular bisectors met at the circumcenter, and that's the point where there was a circle circumscribed, or the triangle was tongue twister. The circle was written outside the triangle. With the incenter, wait for it, I draw a circle, and it meets inside the circle. So there's a circle inside. That's why it's known as the incenter. Pretty clever name, huh? So anytime I have the angle bisectors, this point will be known as the incenter. And the incenter is the point where I can draw the inscribed circle of the triangle. And all that means is the circle is drawn inside all parts of the circle. And since all parts are inside the circle, I know the radii are all the same. And if the radii are all the same, that means from the incenter to the line are all equal distant. So any point from, so the one point from the line to the incenter will all be equal distance. So that's an important feature of the angle bisectors and the incenter to keep in mind. And that'll always be true no matter what kind of triangle we have. So even if I drag the vertices the angle bisectors remain there, and that incenter remains with the circle inscribed within the triangle. Okay, told you it's pretty cool. Anyway, let's continue on and write some information down about the angle bisectors. So the angle bisectors of a triangle intersect at a point that's equidistant from the sides of the triangle. Remember, I can draw this circle inside, and all three of those parts are congruent. So AP, BP, and CP are angle bisectors. So now PD is equal to PE, which is also equal to PF. And so that's the unique thing about those angle bisectors and the incenter. You can read more about it down below. Let's apply that in the diagram. So N is the incenter of ABC. So if that is the case, let's see if I can draw a circle. There we go. So if I can draw the circle inside there, I know that that's going to be congruent. All those segments will be congruent. Now I want to find ND. So ND I will highlight in green. So how am I going to figure that out? Why don't you think about it for a while, pause the video, and then start it when you're ready. All right, so how do I find ND? Well, I notice it's the same as all these. So if I can find any of these that I marked in green, I'll know what I'm looking for. So let me just highlight in blue what I know. I know this is 16, this one's 20. Well, I see that I have a right angle here, so this has to be a right angle. So I have got a right triangle where I know the hypotenuse and I know one of the legs. I just need to find the other leg. Well, I wonder how I can figure that out. Well, I think I learned one time that a squared plus b squared equals c squared. I believe we call that the Pythagorean theorem. And if I just put in the information I have, I can solve the problem. So x squared plus 16 squared equals 20 squared. X squared plus 16 squared, I believe, that's 256. Let me know if I'm wrong. 20 squared is 400. Solve for x. Subtract 256. X squared is 144. Would make x the square root of 144, or 12. So if x is 12, you know, that's 12, that's 12, that's 12. So ND would also have to be 12. All right. So using those rules of logic and applying what you know about the Pythagorean theorem and right triangles, we can figure out the missing lengths using the incenter. So that's all the time we have. Hopefully you learned a little something about angle bisectors and the incenter and the fascinating relationship between the circle and the triangle once again. That's all the time we have. We'll see you next time.